Are you ready?
Yes. Okay, yeah, so this is my project on quantifying performance of quantum teleportation with an arbitrary resource state. And this was done with Dr. Mark Wilde and his graduate student, Vishal Singh. So this has a lot to do with quantum information theory and a lot of information theoretic concepts. So I'll just fix some definitions. So in classical computing, like kind of what we're doing now, the way we're able to communicate, and really the birth of modern technology and stuff like that is based around bits and binary digits, zeros and ones. And there's interesting theorems from Church and Turing, Shannon, about the types of computations and things you can calculate using and or not gates. So these are called universal gates of classical computation. And it's kind of taken for granted sometimes that in a lot of these processes that are going on in the computer or being communicated around on networks and things like that, this classical information, and that's kind of a common term, like for just a binary digit, is classical information. It can be copied, stored, moved, and it can be copied. You can keep a copy and then send it to someone else. And that's very important. Yeah, so now in this new quantum computing, quantum information kind of field, we'll be dealing with quantum bits, which are qubits, and they can perform universal computations, universal logic using 2-qubit logic gates. They're called C0, controlled not, and the Hadamard operators. And these qubits, and this is a little bit of mathematics down here, these qubits can exist in superpositions of 2 independent states. So if you have a 0 and a 1 state, just like in classical computation, these are 2 distinguishable states, but they can exist as a superposition of these 2 states at the same time, I'm kind of saying. But in reality, these are complex. They can take on complex values, these parameters. So they have 2 independent degrees of freedom. And when you start adding more qubits together, the total number of available states increases like 2 to the n instead of linearly, as in Moore's law. So this has been a very interesting field of research in the past few decades. And this is Google's CEO with their quantum computer. It works on this kind of C0 Hadamard architecture. One of the hallmarks of quantum computing and all this kind of quantum information is that qubits cannot be copied. There's a no cloning theorem. So at any point that you want to communicate or pass information around, you can't just copy paste it to someone else or send it in the same kind of file. So it requires one more resource. So that's where this quantum entanglement comes in. And there's a lot you can say about entanglement, but well, I'll just call it entangled. And really, there's entangled qubits. So we'll call them E-bits. And these E-bits can be generated by using our 2 universal gates, which are the Hadamard and the C0 operation here. And by passing two qubits that are in an initial state to these 2 operations, you can create this entangled state where these 2 qubits are now in a pair, and they have this strong correlation that is very fragile from interference from the environment, but also very resourceful and very useful for interesting quantum protocols and quantum information things. So and you can do some things with that in classical computation, but I'd like to consider what you can do with this with networking. So if you want to think of like a quantum internet. So in the analogy to a classical sense, in classical networking, if I have 2 parties here, Alice and Bob, and they're connected over, and here I'll just show like a LAN cable. Now, if Alice has some information on her computer, which is stored somewhere in like RAM or ROM or something, and then she can encode this information, essentially copying it, and it gets encoded onto pulses. If she actually measures the voltage values on that wire. They'll be encoded into there, and then this information will get passed to Bob. But they both retain the same information. Now, in the quantum teleportation, quantum networking case, it takes a little bit more. So initially, if Alice and Bob share one part of this entangled state, so Alice has one part of an E-bit, and then Bob has another part of an E-bit, and Alice has this qubit down here in the lower left that she would like to teleport, then she can use her quantum computer and a classical computer to make a measurement with her classical computer or with her quantum computer, and then make a classical communication to Bob, which he can then use to reconstruct her qubit at the destination. So you use it, and then you've expended an E-bit, and you've used classical communication to reconstruct this qubit. So it's very, very how do you say, unexpected, very interesting. And this is how you'd have to do any kind of communication on a classical computer. So if you had like a quantum memory, which is pretty hard to do, then you'd have to teleport a bit from the memory into processing. Or if I wanted to send the qubit out anywhere, like out to space, and they've done this in experiments, then you have to use this kind of teleportation to do noiseless communication. And this is the same thing. And this is called like a protocol. So if Alice and Bob if Alice would like to teleport this state psi A prime to Bob, then they can share this maximally entangled state. Alice can make a measurement, perform a classical communication to Bob, and then conditional on that communication, Bob can reconstruct her state. And yeah, and then this has been shown since 1993. Yeah, very interesting stuff. So what we've been, yeah. And then this has advantages for increasing, because you can actually do this process backwards and increase your channel capacity. That's one application. If you want to do distributed quantum computing, this is something that you'd have to do for like quantum internet. But in the near term, a lot of things people are interested in is its enhancement towards cybersecurity. So there's a quantum analog to something like public key distribution and RSA. That's called quantum key distribution. And this is an active field of research that will come along at some point fairly soon. And so in our work, we would like to investigate, and we have been investigating, what and how this system or this kind of protocol would work when our E-bits are imperfect. So if there's noise in the system, then we need to correct that, or we need to know what the absolute minimum that we can operate under. And this is a lot of information theory that is already being done in like a classical sense. And so we construct semi-definite programs that can run optimizations to find the optimal solution and the optimal error threshold. And yeah, and this would have some kind of application to quantum error correction and a lot of other kinds of information processing techniques that are necessary to realize this quantum computing future. Yeah. So if anyone has any questions, I'd love to take them.
Yeah, I have a question. So this semi-definite program is a minimization approach?
Yes. So if you're familiar with something like in machine learning, almost how you'll have an objective function, and then you'll have a set of constraints on that objective function, and then you'll want to minimize the objective relative to some set constraints, and that's the same thing that we'll be doing here. But in the semi-definite case, it's called semi-definite because these are matrices and they're not always linear functions.
Okay, and you minimize that not using machine learning. I mean, you minimize that problem using an algorithm.
Yes, numerical solver. Yeah.
Mm-hmm. Okay.
So Theron, go back to the plot that you had of the figure of teleportation.
Here.
So, so Juana, what we're assuming here is that this state here is no longer perfect, and it's subject to noise. And then we want to allow for a minimization over all possible protocols of this form. Those protocols are called one-way local operations and classical communication. It turns out that that class of operations is hard to optimize over in a mathematical sense. And so what we do is we relax the set of operations to include like a larger set that can be characterized with semi-definite constraints. And then when we do so, we can write the error between the ideal. So teleportation realizes an ideal qubit channel from Alice to Bob. So then when we allow for this enlarged class, we can write the error between the ideal case and the actual case as a semi-definite program. The project is similar conceptually to what Eliza Siddiqui and I ended up doing, but we're using a conceptually different way to enlarge these class with this class of operations.
Okay. Okay, thank you.
So, and thank you, Theron, for coming here this summer. It's been an enjoyable experience for me. It's been nice to have you on board, and I look forward to writing a nice research paper with you and Michelle.
Thank you. I've also enjoyed it.